Hey guys, it's me again, and here we go. So this was the first page, I should say, of the homework that you had last night. The joke at the top wasn't really the point, but the first one was a hardened criminal, and the second one was check out lions. But anyway, the correct letters to the answers are all right there. So if you need to, go ahead and pause and take a look and talk out how you got your answers. And then the next page, why was the pail pale? It wasn't a well bucket. And again, there are the correct answers to each of the problems. And if you need to, again, hit pause, talk out how we got them, solve them together as a class, and then go ahead and continue to hit play. Otherwise, just wait a few seconds here. Okay, so here we go. Solving radical expressions, right? So now we're actually going to see how in the world this all is related to actually solving it using equations, okay? So we're going to put everything together. Let's take a look at what we've got here. I'm going to enlarge this a little bit so I can read it. A pole 16 feet tall breaks as shown in the diagram. What is an expression for D in terms of H? And explain your process. So we want to figure out ultimately, what is D? How far away is that the end of the pole, the top of the pole, now that it's snapped off? So if H represents the height of the pole still standing, what algebraic expression represents the length of the pole that is broken off? So in other words, I want to know how long right now is this piece right here. Okay, now this is ultimately a right triangle. Right? We've got a right triangle here. And I'm basically asking you guys, we got to figure out how long that is. That's just what we're going to figure out here. Now remember, the entire pole was 16. Right? The entire pole was 16 and it broke off. H of it is still left standing. So what does D have to, or excuse me, what does the length of that have to be? Right? And so it's going to be 16 minus H. However tall that is, 16, take away that, that's how long that diagonal piece has to be. Let D be the distance between the base of the pole still standing and the tip of the broken pole. How can the Pythagorean theorem relate the pole lengths? Now remember, A squared plus B squared equals C squared. Or in this case, I'm trying to find that bottom one. We'll call that A. Or B, doesn't really matter. And so I could say C squared minus B squared is equal to A squared. So let's see here. What do we know about our right triangle? Well, we know we have H squared, right? We've got H here. And we know this now is 16 minus H. We know that's 16 minus H. So I'm going to have that on here. Plus 16 minus H squared is equal to, no, excuse me, right? That's correctly, I apologize. We know that D squared is equal to 16 minus H squared. There we go, 16 minus H squared. Because, hey, I have to have the A's, the B's, and the C's correct. Well, I want to solve for D. D is what I'm looking for. I got to figure out what that is. So I'm going to subtract the H squared to the other side. So now I have D squared is equal to 16 minus H quantity squared minus H squared. Well, I could kind of work this out and play around with it a bit, couldn't I? So let's see here. 16 minus H squared is 16 minus H times 16 minus H. So 16 times 16 is 256. 16 minus H, negative 16H, and another one of those. And then negative H times negative H is positive H squared. So I ultimately have D squared is equal to that big thing, but I'm going to straighten it up and clean it up a little bit. 256 minus 32H plus H squared minus H squared. Right? But these two cancel out. And so I am left with just that 256 minus 32H. I want to solve for D, not D squared. I want d, not d squared. So I'm going to square root both sides. So d ends up being the square root of 256 minus 32h. And I don't know what that is until I know what h is. I cannot go any further with this problem. Even though, yes, I know the square root of 256, I can't go there with that because I can't find that quite yet. Okay, I suppose we could simplify it a little bit. We know that we could factor out a 16, I suppose. Does that help me at all? Let's see here. If I factor out a 16, I would have what? 16 minus 2h. Oh, does that help me at all? I could take the square root of 16. That's 4 times the square root of 16 minus 2h. That kind of helps a little bit, but I still can't solve any further until I know what h is. So that's all the further we're going to go with that. Okay, let's go to the next page. Solve by isolating the radical. In other words, we just want to solve for x. That's really what we're doing. Solve for x. So what's your first step always have been? Well, first step, add 5 to both sides. Add 5 to both sides. Okay, so now we have the square root of x is equal to 3. And you're like, piece of cake. Now, all this, unit a while back, we were like, hey, how do you unsquare something? Well, now, how do you unsquare root something? Well, we're going to square it. And what you do to one side, you have to do the other. So now I'm going to take x, I'm going to square it. The square root, squaring the square root just gives me x, and then 3 squared gives me 9, and I'm done. Now let's check. Let's check it. The square root of 9 minus 5, does that actually equal negative 2? Right? Does it actually equal negative 2? So this becomes 3 minus 5. Sure enough, it does equal negative 2. I'm happy. Yay! Let's do the same thing with the next one. So your gut instinct says, move the 7 over, and your gut instinct is correct. All right, so now I've got the square root of x is equal to 9. And then you have to undo the square root, which means I need to square both sides. And so when I do that, I end up with x is equal to 81. Again, check it. The square root of 81 plus 7, does that actually equal 16? Well, 9 plus 7, sure enough, it does equal 16. I am a happy camper. Okay, let's go to the next page. So let's see how that shows up in the real world. The time t in seconds it takes for a pendulum of a clock to complete a full swing is approximated by the equation t, which is time, is equal to 2 times the square root of L over 3.3, where L is the length of the pendulum in feet. If the pendulum of a clock completes a full swing in 3 seconds, what is the length of the pendulum? Round to the nearest tenth of a foot. I don't know about you guys, but I actually have a pendulum clock. I actually have 2 at my house, right? So I've got this clock, and in, here's the face of the clock, right? And it tells you what time it is. And you're like, oh, yeah, look, there's the time. And then inside there's probably some glass, right? You probably have a piece of glass in there. And then you see some pendulum thing, right? And it's going to swing back and forth, right? It's going to swing back and forth. And so we're trying to figure out how long is that pendulum? Okay, how long is the pendulum? I don't know if you've ever been to the Museum of Science and Industry. They have a huge one. It's like 3 stories tall, and it tells you the time, and it's sweeping through the sand, and it tells you what time it is by this big, long pendulum. It's in a stairwell. So if you ever get there, check it out. It's kind of cool. Anyway, back to our problem. So we know what? Let's go back through here. We've got our equation. We know length of the pendulum. L is the length of the pendulum. And we know it says that it takes 3 seconds. Takes 3 seconds. So that's our time. That's our t, right? And we want to find the length. We don't know the length in this problem. So let's start off by writing our equation. T is equal to 2 times the square root of L over 3.3. But we have t, so let's plug that in. So 3 equals 2 times the square root of L divided by 3.3. So the first thing I actually have to get rid of is the 2. I've got to get rid of the 2, anything that's not inside the radical. So I'm going to divide everything by 2. And yes, I'm going to do the nasty. I'm going to actually put a decimal down. It kills me to do it, but I have to. So 1.5 is equal to the square root of L divided by 3.3. In order to deal with that 3.3, I've got to get rid of the radical first. Got to get rid of the radical first. So let's square both sides. Let's square both sides. So 1.5 squared, that's like 15 squared, so 2.25 is equal to L over 3.3. This should be simple at this point to solve for solve for L. So I'm going to multiply both sides by 3.3. Those two cancel. And I end up with 7.425 is the length. And it's said to round to the nearest tenth of a foot. So I'm going to say that the length is approximately 7.4 feet. So this is really tall, right? This one's hanging like almost to the ceiling of the room right now. That's how tall or how long this one is. Okay, well, what if it only takes 1 second? What if it takes 1 second? Okay. So let's plug it all in and see what we get. Let's plug it all in, see what we get. So 1 second, I'm actually going to do the terrible thing and actually just write down 0.5 is equal to 2 times the square root of L over 3.3. Okay, now what did we do last time? Last time we divided by 2. Well, what's half of 2? Oh, excuse me, that shouldn't be a 0.5, that should be a 1. My bad, my bad. Now we cut it in half. There we go. Now I have my 0.5. Now I got a 0.5. So 0.5 is equal to the square root of L over 3.3. Then what do we do next? We got to get rid of the radical, so I've got to square both sides. So what you do to one side, you got to do the other. Now I know 5 squared, so that means I probably know 0.5 squared as 0.25. And that's going to be equal to L over 3.3. And then I'm going to multiply both sides by 3.3. Excuse me. And I end up with 0.825 is my length. 0.825 of a foot. 0.83 feet. So let's grab a calculator and do 0.83 times 12. Let's just see how long this is. So that ends up being 9.96 inches. So approximately, right, about 10 inches. So this might be like one of those wall clocks that has like a, you know, like the little cat's tail is swinging back and forth and the cat eyes are zipping back and forth. Maybe that kind of a clock, right? Something that goes really fast. All right, next page. So what do we do if we've got a problem where we have a radical on both sides? Ugh, right? Well, first thing I probably want to do is get rid of the radicals. And what you do to one side, you have to do the other. So I'm going to square both sides. I'm going to square both sides. And so when you square something that's being square rooted, you just get the number that's inside. 5t minus 11, and that is equal to t plus 5. Right? Now, shoot, we did this like at the beginning of the year, right? I'll subtract t the other side. Doesn't really matter. Where you start, I'm going to get what? 4t. And hey, while I'm at it, I might as well add 11 to both sides. And on the other side, I'm going to have 5 plus 11, and I get what? 16. I get 16. and then I divide by 4. And so t is 4. Now let's check it before we go too far, right? 5 times 4 minus 11, and I got to take the square root of that, right? Does that actually equal 4 plus 5 under the other radical? And so on this side, I get the square root of 9, and that equals the square root of 9, which is 3. So it works. I'm a happy camper. Okay, why don't you hit pause for a moment, work on this next one, and let's see if we get the same answer. So I got x equals 7. And so if you did not, go ahead and hit pause. If you guys did, then I'm going to keep going, and I'm going to plug it in and make sure it actually works. If not, hit pause. So 7 times 7, right, minus 4. Does that equal the square root of 5 times 7 plus 10? Right, 7 times 7 is 49, minus 4, so I get the square root of 45. Does that actually equal, this becomes the square root of 35 plus 10, 45. It works. Woo, woo, yay. If not, go back, look to see where you made your mistakes. Okay, so now on the next page, we've got this crazy thing. I've got a vocab term, and it's really quite important for us to understand. It's an extraneous solution. Okay, so you could actually go through, solve the whole problem, get an answer, and it doesn't work. Okay, that's what an extraneous solution is. A solution, even though you did all the math correct, it's a solution that doesn't work. And it's kind of a crazy idea. You're like, hold it, I did everything right. Yeah, but when you plug it back in, you're like, oh, whoops, no, it doesn't work. Uh-oh, we got a problem. Okay, so here we go. Take a look at this first one here. So we've got a radical on one side and not on the other. So the first thing we do actually still have to do is get rid of the radical. So what you do to one side, you have to do the other. So we're going to square both sides. So this negative y times negative y becomes positive y squared. That is going to equal, right, y plus 6 over here on the other side. Well, I've seen problems similar to this before where I've had stuff like this. So I'm going to put everything on the other side, y squared minus y minus 6 all equals 0, because I can factor this. Oh, there they are again, factors. Right? What makes negative 6 and negative 1? What makes negative 6 and negative 1? Negative 3 times 2. Now, because that's a coefficient of 1, I can go straight to the answer. Y minus 3 is one factor. Y plus 2 is the other, right? So that means either y minus 3 equals 0 or y plus 2 equals 0. So y is either 3 or negative 2. Now, every example I've shown you, I have taken my answer and plugged them back in. So let's take the first one. Let's take the first one. Let's plug it in. So I'm going to have negative 3. Does that actually equal the square root of 3 plus 6? 3 plus 6. Right? So I have negative 3. Does that actually equal the square root of 9? Okay, so this looks like it's equal, right? However, we are going to end up with, we need to make this become 3, because when we take the square root of 9, it becomes 3, and it does not equal negative 3. It needs to be positive. Okay, even though we know there's a positive negative 3, it needs to be the positive of it. So we can do the exact same thing if we plug in the negative 2, right? Negative, negative 2. Does that equal the square root of negative 2 plus 6? Well, negative negative 2 is positive 2, and sure enough, that does equal the square root of 4 because 2 equals 2. So this one works, this one does not. Okay, so this is not a solution, it's extraneous. The negative 2 does work. So you do have to go back and check to see if your answers work. Let's try that with this last one. Let's try this last one. 6 minus 2x equals 10. Now, before we go too far into this, when have you ever subtracted 6 minus something gives you a bigger number? Well, what kind of number gives you a bigger number when you subtract? So it's going to have to be negative. Okay, just have that in the back of your mind, but we're going to go through and solve this. Okay, so first thing you're going to do, you're going to subtract 6. So we now have negative square root of 2x is equal to 4, right? And I'm going to divide by negative 1 just to get rid of the negative. So now I have the square root of 2x is equal to negative 4. Let's square both sides. Let's square both sides. So you have 2x is equal to 16, right? Negative 4 times negative 4 is positive 16. Divided by 2, and x equals 8. And you're like, awesome. All right, let's plug it in, check it. So 6 minus the square root of 2 times 8 equals 10. So 6 minus the square root of 16 equals 10. 6 minus 4 does not equal 10. So this is extraneous. Now remember I said, this was going to have to be negative. Needs to be negative. We don't know how to deal with a negative x inside the radical. That's algebra 2. Okay, so that's why we didn't get a solution. There is one out there. It's just not a real number. All right, you guys are going to do the homework, the evens, on the next page, and I will see you guys later.